thank you to Henson Shaving for supporting PBS.
This is what's left of the moment the world ended. We can see it right here in the rock, in this riverbank. In fact, we can see it all over the world, where scientists have found evidence of a day so violent it erased 3/4 of life on Earth, including every non-bird dinosaur. It might not look like much, but this changed the course of our planet. But how do we know what happened minute by minute on a day 66 million years ago? Because here's the thing, right? You've seen the recreations. A dinosaur's looking up at the sky, a big rock hits, boom, everything dies. But the reality is so much more interesting and violent. This wasn't just an explosion, okay? The sky literally fell and was followed by centuries of doom. But the craziest part isn't that it happened, it's that we can see it. Today, we're gonna read this story of epic destruction that's written in layers of mud and ash and rock to learn what it looked, sounded, and felt like to live through the last day of the dinosaurs.
"66 million years ago, the day began like any other day. The apex creatures of the Cretaceous, dinosaurs, pterosaurs, and more, doing what big ancient reptiles do. But out there, in the cold, dark vacuum of space, a wandering asteroid from the Kuiper Belt was minding its own business. This hunk of carbonaceous chondrite had passed through Earth's orbit for millions of years without incident, until a tiny gravitational bump set it on a fateful course.
It was a Tuesday, or maybe a Friday, whatever, it doesn't matter. They didn't have calendars back then. But we do know from the fossil record that it was probably early spring. Up there, about 12 hours before the end of the world, an asteroid 6 to 9 miles in diameter, that's wider than Mount Everest is tall, was hurtling through space at 12 miles per second. If you were a dinosaur looking up at the sky, you'd see what looked like a bright star in the northeast.
We would see something getting bigger and bigger. Something that starts out like a small star that gets to be the size of the sun, that gets to be the size of a really big harvest moon, that gets to be bigger than any moon you've ever seen. Right
until it's just taking up the entire sky.
Taking up a huge area of the sky.
And then that's the last thing you see.
And this is where it was about to strike. 66 million years ago, at the end of the Cretaceous, what we now call the Yucatan Peninsula was a shallow tropical sea teeming with life. It was a paradise.
And it was also, geologically speaking, the worst possible place on Earth for this asteroid to hit. Okay, so the asteroid is about to hit Earth. It's entering our atmosphere so fast that the air in front of it is being compressed and heated. The temperature's hotter than the surface of the sun. The air turns into a superheated plasma shockwave. That means before the rock even touches the surface of the Earth, that gorgeous shallow sea of the Yucatan probably vaporized. When it actually hits, the asteroid touches down with the force of more than 100 trillion freight trains, crashing at full speed, all at the exact same moment in the exact same place. If you're like, that sounds bad, I'd like to see what that did to the Earth. Well, you'd need to drill deep into the Earth's crust and pull out a big chunk of that crust that shows all the layers where the asteroid hit. Something like these, maybe.
These are core samples. They're basically cross-sections of rock pulled from deep within the crust. They contain a continuous geological history, layer by layer, from the recent surface down into deep time. This building houses nearly 100 linear miles of core samples. Geologist Sean Gulick led an expedition to the Yucatan to drill these cores from inside the asteroid crater to reconstruct each moment of the impact and extinction that followed.
Cores are a record of what happened on our planet.
And these cores are special because they show a telescoping record of time, giving us a high-resolution view of a single moment 66 million years ago.
So when we look at a normal layer, like if I'm at the Grand Canyon or something, how much time am I looking at in, say, a foot?
So that could be easily millions of years, or even sometimes tens of millions of years.
How does that compare to what we see in front of us here?
We've got about 500 feet that represent less than one day.
So we can read through these to get a play-by-play of exactly what happened moment by moment.
Exactly. So as this 7-mile wide asteroid hits the surface of the Earth, That's vaporized immediately. Those first layers of rock, they're also vaporized and ejected out into the atmosphere. And that vaporization and ejection depth goes all the way down, hundreds and hundreds of feet. What's below that, then, instead of vaporizing the rock, melts. This is what is called melt rock, very simply. This is actually granite that instantaneously hit enough pressure to turn to a liquid and is now solidified into a rock.
So it's not like it took a few seconds. It was solid rock in one moment, and then it's just instantaneously melts. Next, the atmosphere literally ignites. Now, one of the most destructive forces ever unleashed during our species' time here on Earth is the atomic bomb. Now imagine almost 9 billion of those bombs exploding at once. That thermal radiation travels at the speed of light across the Earth, instantly incinerating everything within 600 to 1,000 miles. Every bit of organic material within that range was scorched like that. That much energy impacting the Earth all at once vaporizes most of the asteroid. The Earth's crust stops acting like rock and starts acting like a liquid.
That shock wave, it is moving through the Earth at the speed of sound of the rock, so kilometers per second. And what you have is granite that has been shocked. And if it hits something very fine grain, it makes something you can visually see with your eye. These are called shatter cones. And you can see this almost fractal pattern on the surface of this fine grain material. It's like runaway earthquakes in a fan-shaped pattern. These are direct, visible evidence of what a shockwave does to fine grain rocks.
The only way those can happen is from a kinetic impact like this.
Right, a hypervelocity impact coming in, 20 kilometers per second. 10 to the 23 joules kind of energy is the only way to make these kinds of features. These are effectively proof positive that it had to be a hypervelocity impact to make them. And it's actually kind of amazing that we just sort of randomly caught one of these in a core that's only this wide.
That's pretty lucky.
Yeah.
Just like when you drop a pebble into water and that little jet of water shoots up in the middle, the Earth did that. So granite that was once miles underground was suddenly and violently pushed upward through the Earth's crust and up into the air, nearly 12 miles into the atmosphere. In fact, it's theoretically possible that pulverized dinosaur dust ended up on the moon. I don't know, we haven't found any, but it could be there. This rock then collapsed outward to form a ring of small peaks around the crater, what we now call the peak ring. Now, these formations were hundreds of meters high, and this all happened in less time it takes to boil an egg.
So the peak ring is made, this granitic peak ring is made in about 5 minutes, and this is then the minutes to hours of material laid on top of that.
Because what goes up must come down. Here in what is now East Texas, 800 or so miles from the Chicxulub crater, we can see exactly where the billions of tons of rock that were sent up into the atmosphere by the impact came raining back down to Earth.
These are called spherules, and they come from the vapor plume from the ejecta coming in a giant, fast-moving cloud across the landscape. So it actually has the speed and the energy and the amount of stuff to go all the way around the whole world.
Oh, wow.
But as it's hitting the ground is not stable because the earthquakes have also erupted.
We're having like
a bad day.
A Richter 12 earthquake.
Yeah, magnitude 11 is some of the estimates. Certainly it's over a 10, which is larger than any fault on Earth can do, because we have no singular fault that's ever going to be big enough to make it bigger than a 9 something. Okay. And in this case, so we're shaking, probably the ground is moving up and down on the scale of 6 to 10 feet, rolling as it goes by. This cloud is moving in and raining. It's hitting water, because we're under the water, raining down on us, and then the water itself becomes a wave because the tsunami arrives.
Yeah, you heard that right, a tsunami. The hole punched into the Earth's crust by the asteroid evacuated billions of tons of water, which set off a mega tsunami that struck every coastal area on Earth.
Remember, 66 million years ago, before the asteroid hit, all of this was underwater. And if you look at these layers here, you see something weird. Big chunks of mud and sand that were ripped off the bottom of the ocean and deposited here, far away from where they'd originally come from.
What we're standing on is a mudstone like you'd see on a continental shelf, seafloor anywhere. But then suddenly this thing that makes a cliff is a different set of processes.
This simulation of the tsunami caused by the Chicxulub impact shows waves a mile high, which means almost every coastal area on Earth would have experienced catastrophic flooding.
The tsunami is so big that it's nothing for the bottom of that wave to be tearing things up as it comes. In other words, the seafloor is actually feeling the bottom of the wave because it's so high on the top. So
scooping up plowing everything in its path.
Scraping, mixing, so on, and it comes up on the edge of the shelf and it crosses the shelf where we're standing right now, deposits in these crazy contorted looking beds. And it's not just one single tsunami, right? It's a train of waves coming one after the other.
So water never moves just once, right? There's always a back and forth. Think of like a splash in your bathtub or the swimming pool. So while mile-high tsunami waves are crashing down all over the world, what's happening inside the impact crater is even more interesting.
We have the tsunami leaving, but all the water that it's pushed out of the way doesn't all leave. In fact, the bottom part of that collapses back into the crater. And when it hits this molten rock, it actually explodes. And eventually that explosion component goes away and you just fill the crater with what is very dirty water. We've got roughly 300 feet of material that is just the material that rained out of this cloud of debris inside the crater. At the very top of it is the tsunami that left the crater, bounces off land and comes back and leaves a record of it in this one section of the core here.
So all the stuff that got burned up instantly gets washed back. So this is like burned dinosaurs and plants and...
There's a record of charcoal within this.
Wow. Burned extinction charcoal. It's amazing. Believe it or not, the firestorm, the tsunami, that was all just the opening act to the extinction. They were enough to make pretty short work of any dinosaurs surrounding the impact site, but if that were all it was, many dinosaurs would have survived. Who knows what kind of crazy creatures we'd have walking around today. But what followed was a swing between climate extremes that was so severe it killed most life on Earth. First came the impact winter. Dust and soot were ejected from the impact and formed a dark layer in our atmosphere, blocking out the sun and dropping global temperatures by as much as 50 degrees Fahrenheit.
And by this point, you're dark and you're not...
Permanent night.
Permanent night, you're not doing photosynthesis.
And for cold-blooded reptiles used to this tropical paradise, that was a death sentence. They simply didn't have the metabolism to survive a deep freeze that lasted nearly 20 years.
Along with the soot and ash from the impact darkening the sun, the impact also vaporized sulfur-rich rocks, creating sulfate aerosols in the upper atmosphere, which blocked even more sunlight.
Photosynthesis was in deep trouble in this dark, cold planet. That probably contributed to a massive die-off of plants that dinosaurs depended on. The dinosaurs that ate the plants started to starve, and as those dinosaurs starved, so did the dinosaurs that ate them. At this point, ocean plankton begins to die off too. These are the organisms at the very base of the global food chain. They can no longer survive, which means not much else is going to survive either. But after several decades, that long winter slowly starts to clear. But things got pretty extreme in a different way. You remember where the asteroid hit? The rock that the Yucatan sits on is made of limestone, which is calcium carbonate. When the asteroid struck, it vaporized those rocks and injected roughly 400 billion tons of CO2 into the atmosphere instantly.
That sediment gives you the material to put into the atmosphere to change climate. But if it had hit in a different place, if it had hit 30 seconds earlier or 30 seconds later, it would have hit the Atlantic Ocean or the Pacific Ocean. All that would have gone into the atmosphere would be water vapor. It wouldn't have been an extinction event.
And we wouldn't be here.
Yeah,
This show would be hosted by a dinosaur, is what we're saying. That's what we're saying.
That's what we're saying.
That means once that sulfur haze cleared and the sun came back out, that CO2 trapped the heat, flipping the Earth from a freezer directly into this super greenhouse sauna that lasted for thousands of years. Now, dinosaurs were used to a hot world. That probably wouldn't have been enough to kill them off if it hadn't been for that sort of kill every plant on Earth winter that happened right before. So, dinosaurs, really bad time for dinosaurs. Not any dinosaurs.
Right.
Over the next couple thousand years, one by one, every single non-bird dinosaur and pterosaur and other kinds of saurs, all the cool reptiles that dominated the Earth die. Lack of habitat, lack of food, lack of warmth, then way too much warmth, cataclysmic droughts. The whole world became inhospitable to them, and only their bones remained.
Here's the thing. Geologists and paleontologists knew for decades that a major extinction event had occurred between the Cretaceous and Paleogene eras of geologic time. Before this boundary, we see dinosaur fossils. And after, well, not so much. They just didn't know why. But back in the 80s, a geologist named Walter Alvarez noticed that there was this layer of clay that was pretty much the same age and it was pretty consistent across many sites around the world.
With the help of his father Luis, who was a famous physicist, Walter Alvarez discovered that this layer had super high levels of an element called iridium.
In Europe, South America, North America, even New Zealand, you can see that same layer dating to the same moment.
The thing about iridium is it's rare on Earth's surface, but it's common in asteroids, and this was the critical clue.
And that immediately led them to the hypothesis, wow, this thing is global. The only way that's possible is it was a really big asteroid. So once this iridium layer was found, the question was, where is the crater that should be left behind by an asteroid that's 7 miles wide? It turns out that the impact crater had been discovered in the 1950s.
Enter Glenn Penfield and Antonio Camargo. They're geophysicists looking for oil in the Yucatan. They were using magnetic data as part of their mapping, and they found this massive magnetic anomaly, basically a perfect bullseye off the tip of the Yucatan Peninsula. They took it to their bosses at the oil company. They even published their results. But see, they were presenting at an oil and gas conference while all the geologists who were looking for the crater over at the nerdy We Love Rocks conference, so none of them heard about this discovery. A local news reporter even covered their talk in a front page story, and Penfield wrote to Alvarez to say he thought he'd found the crater that Alvarez was looking for, but got nothing in return. All the puzzle pieces were there, but they didn't come together for decades.
It was Penfield and Camargo and then others who joined them later like Alan Hildebrand who put the pieces together. We said, here's this low density anomaly that's huge, 200 kilometers across, 125 miles across, and here's some cores with material that clearly came from an impact. This must be an impact, and this must be the one that's tied to the extinction event 66 million years ago.
From Mexico to Denmark to New Zealand, this thin, dark line in geologic time tells the story of a day that changed the world forever and made dinosaurs a thing of the past. Elsewhere on Earth before the impact, other bad things were happening. In what's now India, 1 million years of massive volcanic eruptions had been spewing climate-changing gases into the atmosphere. But thanks to these impact cores, the vast majority of geologists now agree that it was the asteroid and its effects that ended the age of the dinosaurs.
It took something much greater, something much more rapid, like an impact, to actually cause the extinction event.
In the years and centuries after the Great Darkening, light gradually returns. But what plays out in the aftermath is way different than when it dominated the Earth before the impact. On land, we see a fern spike. Most of what's preserved in the land fossil record immediately after the impact layer are ferns. In the oceans, turns out they bounced back surprisingly fast.
When we look in detail, what was actually dominating the waters in the crater was algae. So things like cyanobacteria, some of the very earliest kinds of life form on Earth, were able to live in this sort of empty ocean where most of the plankton are gone, 90% of the plankton are gone, so these early picoplankton, as we call them, actually take over. And they probably dominate the oceans for 200,000 years.
You can't keep a microbe down. Back on land, within 100,000 years, palm forests took over, and mammals doubled in size thanks to all of that new food. By 300,000 years, we see the first appearance of trees in what will eventually become the walnut family. And mammals got even bigger, up to the size of a beaver. And by 700,000 years, we see the bean family appear for the first time. With all this protein-rich plant material, mammals exploded in size. They got up to 100 times heavier than they were in the age of the dinosaurs. We humans may even have had our very distant origins here. Meet Purgatorius. Fossils found in Montana, dating to just 100,000 years after the impact, reveal this tiny little chipmunk-sized creature, and it was already thriving. It's the oldest known member of the group that gave rise to all of the primates, lemurs, monkeys, apes, and eventually us. We all started in this moment. Purgatorius may have existed in the final days of the dinosaurs, but the extinction of the dinosaurs completely changed the trajectory of evolution of both plants and animals, clearing their way for the rise of the mammals. So, in a very real way, the only reason that you're here to watch this video is because that little guy survived the apocalypse. Ultimately, the story of the dinosaurs' last day on Earth is one that we can learn from too. Our planet has rewritten its rules before. Rapid, global, cataclysmic change is not a hypothetical thing. It has happened, and when it did, life had to reinvent itself. The story of that day isn't just about extinction, it's also about resilience and adaptation. This is a pivotal point of life on Earth. Everything above it, us, all of our ancestors, our ecosystems, that all exists because of everything below it disappearing. But there is a warning here too. The changes that we see in the rocks, rapid CO2 spikes, ocean acidification, collapsing food webs, are eerily similar to what we are measuring today.
It's the speed of things that evolution can't keep up with. The estimate is we're in the 6th mass extinction event because of changing the atmosphere. I think the lesson for today is that if you change the atmosphere rapidly, life can't keep up and you will get an extinction event.
Now, the dinosaurs didn't have a choice, but we do. Stay curious.
And thank you to Henson Shaving for supporting PBS. Henson Shaving is the maker of the AL13 safety razor. When it comes to shaving, data probably is not the first word that comes to mind, but using research and data, Henson wants to help users. Henson partnered with a medical imaging startup that lets them quantify the impact of their razors and analyze the skin's reaction to shaving with different razors. Plus, the AL13 uses a plastic-free, all-aluminum design manufactured in an aerospace machine shop using CNC machines. To learn more, visit hensonshaving.com/PBS and use code BESMART to get 100 blades for free with your purchase of a Henson razor. Just be sure to add it to your cart. And a huge thank you to everyone who supports the show on Patreon. We love to be able to go to the places and see the things behind these science stories, like those incredible drilling cores or that awesome site next to the river that shows where the impact came in. We could not do that without the support of our patrons, and thank you. Just like these fine people at our top tier, you can join that community by heading down to the link in the description. We'll see you in the next video, assuming nothing falls from space in the meantime. I hope not.
That was fun. That much energy. Yeah, I almost fell over. Okay. You can't move it when it's on the cart.